Okay, hi everyone. So today we have Yuxi Han, who is currently PhD student at UW-Madison. She gonna present on the optimal rates of conversion in periodic homogenizations of convex Hamilton-Jacobi equations with multiscales. Please, Yuxi.
Thank you. Hi, everyone. Thanks for coming to this online student PD seminar for my talk. Today, I would like to talk about a recent work with my collaborator, Jiwon Zhang, on homogenization for Hamilton-Jacobi equations. So homogenization lies in the intersection of four fields, which are PDE, dynamical systems, first passage calculation, and metric geometry. Today, we are going to look at the rate of convergence in periodic homogenization for convex Hamilton-Jacobi equations with multiscales. And surprisingly, this is closely related to metric geometry, as we will see in a second. First, I would like to go over the outline of my talk today. So I will talk about some basics for homogenization of Hamilton-Jacobi equations first. And then after that, I will introduce some recent development about rate of convergence. In particular, we will go over the case where the Hamiltonian only depends on the oscillatory variable y and the generalized momentum p. And in that case, the optimal rate of convergence is O epsilon. And then after that, I will introduce our main results for the case where Hamiltonian can also depend on the spatial variable x, and we will go over the proof ideal briefly. Okay, before diving into those topics, let's take a look at a problem in geometry, which is front propagation. In this problem, imagine we have an n-dimensional manifold. In this picture, it is a special case and it's a curve. And on this manifold, every point is moving according to some given rules. In particular, we require every point on the manifold is moving in the normal direction at the speed of a given function a of x. A natural question is to study how the manifold is evolving according to the time. And so here we have the level set method for this problem. And this level set method was first raised by Osher and Sassian in 1988. And suppose we have a function u which takes in spatial variable x and time t, and its zero level set at some particular time t is exactly our manifold at that specific time. And moreover, we assume our function u is less than zero inside the manifold, and also it's greater than zero outside the manifold. And in this case, we can actually write down the normal vector in terms of u, which is du over the magnitude of du. So here du is the gradient of our function u. And after the calculation, we can deduce u actually solves the following PDE, and ax appears in front of the absolute value of du. And this is the level set method for front propagation problem. However, in the reality, the situation is more complicated. Imagine we are trying to study, say, the forest fire in California, and we can look down at the fire region through a helicopter or a telescope. Then usually, we can see the edge of or the front of the fire region is not smooth, as shown in the picture on the left. And it usually comes with the zigzag parts. If we still use the previous front propagation model, we can write down a similar PDE on the left. Here we can see we have, instead of a of x, we have a of x over epsilon. This epsilon is actually the small scale associated with this picture. So when we are looking down from our helicopter or the telescope, there is always a fixed scale associated with our picture, and it depends on the, say, the height of our helicopter or the accuracy of our telescope. And because of this small scale, when we are trying to study the PDE on the left, it's very complicated and costly to compute the numerics for this PDE. So a natural thought is we want to simplify this picture. And in fact, we only care about the motion of the effective front of our file region, and we don't really care about the motion of the zigzag parts. So the solution is we will introduce homogenization, which is we let epsilon tending to 0. And so we can see the picture on the right. We hope as epsilon tending to 0 in the limit, we will have a nicer PDE, and which is easier to solve using numerics. And it turns out it is the case. Okay, so next I will talk about the setting for our homogenization for Hamilton-Jacobi equations in detail. So we define a function h, which is called the Hamiltonian, and it has 3 inputs, x, y, and p. So here x is called the macro scale variable, and y is called micro scale variable. So here the variable y takes in values in the n-dimensional torus, and it captures the zigzag part we see in the previous picture. So usually it's periodic. And the variable p is the generalized momentum, and it takes value in Rn. And there are 2 assumptions for our function h, which we also call Hamiltonian. So first assumption is we assume h is BUC. Here BUC stands for bounded uniformly continuous. So if our generalized momentum p is bounded in some ball of radius r, we assume h is bounded uniformly continuous on that region. And besides, we also assume our Hamiltonian is uniformly coercive in the momentum. That means as the magnitude of p tending to infinity, the function h is also tending to infinity uniformly in x and y. Okay, so these are the 2 assumptions for our Hamiltonian. And then let's look at the Cauchy problem. So we let epsilon greater than 0, and u epsilon is the viscosity solution for the following Cauchy problem. The initial condition is given by some function g, and our Hamiltonian h appears in the equation. And notice the second slot for our Hamiltonian is x over epsilon. So this slot captures the zigzag part we saw before. And we hope to let epsilon tending to 0 and get something simpler. So indeed, in 1987, Lyons, Papanicolaou, Varenham, they proved u epsilon converges locally uniformly to some function u, which is the solution to the following Cauchy problem. This equation has the same initial condition g as we started with, but the Hamiltonian is much simpler. So here we have a new Hamiltonian, which I denote by h bar. H bar is often called effective Hamiltonian. It's uniquely determined by our original Hamiltonian h. And we can see h bar does not depend on the oscillatory variable y anymore. It only depends on x and the momentum. And also the way that h bar depends on h is highly nonlinear, and we are not discussing it today due to the time limit. So the question we are interested in today is how fast u epsilon is converging to u as epsilon tending to 0. So next, I'm going to show you some recent development about the rate of convergence for Hamilton-Jacobi equations. So for general non-convex Hamiltonians with multiscales, it was first studied by Capuccio, Dichata, and Ishii in 2001, they proved the rate of convergence is O epsilon to 1/3. And the method they used was doubling variable. And they didn't prove whether this O epsilon to the 1/3 is optimal or not. And after that, for a special type of Hamiltonians where H is convex in the momentum P, and it doesn't depend on X, so it only depends on the oscillatory variable Y, which is a micro scale variable. It was first studied by Mitake, Chuan, Yu in 2018. They proved the lower bound is optimal for the rate of convergence. In particular, they showed U epsilon is greater than or equal to U minus some constant C times epsilon for all X and T in the domain. And for the other upper bound, they had to put more conditions. And later in 2021, Chuan Yu proved the optimal rate for the previous Hamiltonian is actually O epsilon. And in particular, we have the following result. So one thing we should notice here is this O epsilon rate, or the constant C in front of epsilon here, is uniform in time t. So this is actually different from our situation where H depends on X. We will see in a second in our result, the rate of convergence actually depends on the time t, but here it's uniform in time. So the main idea for them was to use the optimal control formula for the solutions U epsilon and U, and together with a topological lemma on decompositions of curves from metric geometry by Barago. Sorry, Barago. So that's for the case where the Hamiltonian does not depend on X. And for the general Hamiltonians that can depend on X, in 2022 proved the optimal rate for one dimension with conditional assumptions on the Hamiltonian is O epsilon. So our work shows for this situation, we can do it for a higher dimension, and the rate of convergence is actually O square root of epsilon. Okay, so next I will show you our main result. For the assumption, besides the two assumptions we mentioned just now, we have to assume two more assumptions. So here, H3 is the assumption about H is convex in the momentum term. And H4 is the assumption about the Lipschitz-ness of our Hamiltonian. In particular, H is Lipschitz in the first slot uniformly in Y and P. And we can actually show the Lagrange transform for H, which we call L, and the Lagrange transform for H bar, which we call L bar, have the same properties of H3 and H4, which means L and L bar are convex in V, and they are uniform Lipschitz in X. So L and L bar will come up in a second in our proof, typically in the optimal control formula for our solutions. And moreover, for the assumption H4, we have a particular example in our paper that shows it's a necessary condition. If we don't have H4, then our conclusion is simply not true, and the rate of convergence is much slower. Okay, so here is our first result for the Cauchy problem. We assume the previous assumption H1 up to H4, and our initial condition is bounded uniformly continuous and Lipschitz. We let epsilon greater than 0, then we have the following rate of convergence. And we can see this rate of convergence actually depends on whether the time is greater than or less than square root of epsilon. So if our time is greater than or equal to square root of epsilon, we have the rate of convergence of O t square root of epsilon. If t is very small, smaller than square root of epsilon, then we have something a little bit better, which is the minimum of t comma epsilon. And this rate of convergence is actually related to quantifying the averaging of metric to its limit in metric geometry, which we will see in a second in the proof. Moreover, we prove that the rate of convergence is optimal, at least for the time t between 0 and square root of epsilon, and about the O square root of epsilon order. For the whole range of our time t, we don't know if our rate of convergence is optimal or not. So this is our first result about Cauchy problem. And then here is the second result about the static problem. We basically have the same assumption, and we have an actual letter lambda greater than 0. This is the fixed constant we have for the monotone term in the PDEs here. And U epsilon and U are still the solutions to the corresponding equation with epsilon and the limiting equation. We can show the convergence rate is still O square root of epsilon. And in today's talk, I will mainly show the proof for Cauchy problem. So the proof for the static problem is basically the same. So let's return back to our Cauchy problem result, theorem 1. And the proof idea is still using optimal control formulas. And besides, we are going to use something called separating scales. And this is the first time for us to see separating scales in the level of optimal control path. And basically, separating scales means we will treat the macro scale and micro scale variables separately. We will fix the macro scale variable and averaging out the small scale variable. And besides that, we will use some curve cutting techniques we will see in a second. And also we build our result upon optimal rate of O epsilon for the special case where H does not depend on X. Since we are building upon on this previous result, we will first review the proof for that. Okay, so here is the Cauchy problem for the special case where my H does not depend on X. So we have a similar Cauchy problem. In this case, H only depends on X over epsilon and du epsilon. And we can write down the optimal control formula for the solution U epsilon. So here we take a point X in our domain Rn, and we consider any absolute continuous path. So here AC stands for absolute continuous. So we consider any absolutely continuous path that ends at the point X, and time runs from 0 up to time t. And we compute the corresponding total cost. The cost consists of two parts. One part is the integral of L, where L is the Lagrange transform of H. And then the other cost is associated with our initial condition G, which is called initial cost. So we will focus on the running cost. And you can see here inside the first slot of L, we have the dependence on epsilon. So when we send epsilon to 0, the dependence on our path c and how our cost is changing is not clear. So in order to make the formula easier, we do the following change of variable. So here we let a new path gamma to be the following. We take the previous path c, we rescale the time by epsilon and divide the whole thing by epsilon. So after the change of variable, we have our path that starts from the time 0 and take time up to t over epsilon. And the ending point becomes x over epsilon. And another thing to notice is we have an actual factor epsilon in front of the integral. Okay, but the good thing is we no longer have the dependence of epsilon inside the slots of L here. And this will help us to see the proof easier. Okay, so we will look at the first term here. And we define a new function m. So this m has 3 inputs, t, y, x. So basically m is the minimum cost for us to go from the point y to x using time t. And the cost is computed by the integral of our L function and integrate from 0 up to the time t. And we can view this function m as a metric. So it basically measures the cost for you to go from y to x in time t. And with this new notation, we can rewrite the first term in our formula here. Suppose we assume the path starts at the point y over epsilon. Then we can write the first term, the integral in terms of m, as epsilon times m of t over epsilon, comma y over epsilon, comma x over epsilon. And we can change the initial condition for, the value inside g to be y. Okay, so by default, actually, we should consider all starting point y in Rn. But we actually have an a priori estimates for u epsilon. And from there, we can show the velocity of minimizing curves are actually bounded. So instead of looking at all possible starting point in Rn, we can only look at the starting point y, which are distance c times t away from x. Excuse me. And we only need to take the infimum over all such y, not all y in Rn. Okay, so this is the optimal control formula for u epsilon. Next, let's look at the limiting equation. So for limiting equation, in this case, h bar does not depend on x anymore. It only depends on du. And we can still write down the optimal control formula for our solution u. So here the rounding cost is taken as the integral of L bar, and L bar only depends on the velocity of your curve. So my curve eta is still using time t to go from the initial point eta of 0 to the point x. And we are taking the infimum of all possible total costs over all possible such curve. And now we can see that since our Hamiltonian is convex in P, we can show our L bar is also convex. And besides, L bar only depends on the velocity. So by the Hall-Flex formula, which says if your L only depends on one variable and it's convex, we instead of looking at all possible paths eta, we only need to look at the straight lines. So the first integral becomes t times L bar of x minus y over t. Here x minus y over t is just the velocity of straight line going from y to x within time t. So this simplifies our formula a lot. And again, we don't have to consider any y starting point y in Rn. We only need to consider the y's such that they are within c times t distance with from our x. And this constant c here can be viewed as the upper bound for the velocity of our optimal path. Okay, now we have both the formula for optimal control formula for u and u epsilon. And we want to find the rate of convergence. So if we compare the two formulas, we can see they only differ at the first term. So in other words, if we can show the rate of convergence for the terms inside the circles, then we can deduce the convergence rate for U epsilon and U. And if we take a closer look at the term in the second circle, the U epsilon M, this is actually averaging of metric, because M is a metric and we rescale the time and starting point by epsilon, and we multiply epsilon in front. When we send epsilon to 0, this is the averaging of metric, and we hope it will converge to what we expect above here, which is T times L bar of X minus Y over T. And we want to quantify how fast is this averaging metric converging to the limit. Okay, in fact, it does converge. So in 1987, Lyons, Papanicolaou, Varenham, they proved the limit of epsilon times M as epsilon tending to 0 exists. And if we call this limit as M bar, it's equal to what we expect, which is T times L bar. And moreover, in the paper of Tran Yu, they proved the rate of convergence for the averaging metric to the limit is O epsilon. So in particular, we let the constant M sub 0 greater than 0. Okay, so we can think of M0 as the upper bound for the velocity of optimal path. Then for any X and Y in Rn and epsilon T greater than 0, if we have X and Y, they are distance less than M0 T apart from each other, then we can show the absolute value of epsilon M and T times L bar is less than or equal to the constant times epsilon. And here, this constant only depends on the dimension, the M0, which is the upper bound for our velocity of the optimal path, and the Hamiltonian. Okay, so this theorem actually, if we want to prove this theorem, we need to use some properties of our M function, the metric, in particular, the subadditivity and superadditivity of our M function. And at the end of this talk, I will go over the superadditivity of our metric. The subadditivity is similar. So from this theorem, we know that the first terms in our optimal control formula for U epsilon and U are converging at rate of O epsilon. It's not hard to deduce that our solutions U epsilon is converging to U in the rate of O epsilon. Okay, so let's return to our case where the Hamiltonian can depend on X, the spatial variable. And we can still similarly write down the optimal control formula. In this case, L has an actual dependence on Cauchy in the first slot. And in the second slot, we still have Cauchy over epsilon. We can do the change of variable again, try to make the formula easier. But in this case, after the change of variable, we can see epsilon still appears in the first slot of our L in the integral. So it doesn't really help. And moreover, we can write down the optimal control formula for U in the limit. And we can see L bar has the actual dependence on eta. So the Hoff-Lax formula no longer works. So indeed, this actual dependence causes a lot of trouble here. So how can we handle this problem? Well, a natural thought is we want to fix the first slot. So if the first slot is a constant, then we can use the previous result for the case where H does not depend on X. But if we really say fix the first slot to be a constant along any optimal path, then we are going to introduce a large error term. So we have to balance out this and choose our constant wisely. And in a second, you will see the brief idea is we will cut our optimal path into smaller pieces, and inside each smaller piece, we will fix the first slot. And in this way, we can minimize the error cost by fixing the macro scale variable here. So before we do the actual proof, we have to define something. This is the metric function we already seen, but it has an actual dependence on the little c here. So we have the notation m super little c of t comma a comma b. So this is still the cost for us to go from a to b using time t. The superscript little c stands for the first slot, the value inside here for our integral L. Okay, so this is our new metric function. And similarly, we can show the following result for the convergence of the averaging metric to the limit. And we can show the constant c is actually independent of our little c. So in particular, we need to go over the proof that is done by Chuan Yu in 2021. And we explicitly show that the constant big C here in the convergence rate O epsilon does not depend on the little c value inside L. And this actually is very important because like I mentioned just now, in a second, we will cut our optimal paths into small pieces. And for each piece, we will have different little c values. And I want them to converge uniformly, no matter which little c value is there. So we have to make sure the theorem works for any little c uniformly. Okay, so next I will show you guys the proof idea for our result. And I will only show one direction, which is for the time t greater than square root of epsilon, we have u epsilon minus u is greater than or equal to minus some constant c times the time t and square root of epsilon. And the other direction are very similar. Okay, so let's do this direction. And we start with the optimal control formula for u epsilon, and we find a optimal path, we call it gamma. So which means u epsilon is equal to the total cost when we plug in gamma inside. We will focus on the first running cost here. Like I mentioned, because of the first slot is depending on epsilon, depending on gamma, it's not easy for us to estimate. Our idea is to fix it. So in order to do this, we cut the curve gamma into n pieces. Okay, so here, the picture I have here is the curve gamma, and the time is t over epsilon. And we cut it into n pieces. Here, the n is to be determined. We don't know yet what's the optimal pieces we need so that we can have the minimized error. Okay, so n is to be determined. And then if we look at the case piece here, the case piece has the time going from kt over epsilon n up to k plus 1 times the time t over epsilon n. And k can take value 0 up to n minus 1. So for each piece, I'm going to replace epsilon gamma by gamma of kt over epsilon n, which means I'm using the value for gamma at the starting point to plugging in for the first slot in L. Okay, in particular, I break the whole integral into n pieces according to the time. And for the case piece, I plug it in as we have here. Okay, but when we do this, we introduce some error term. So next we are going to estimate the error for this fixing first variable in L, which is the macro scale variable. Here we can compare the first slot inside L, and using the fact that we know gamma dot is bounded. So the velocity of gamma is bounded. And when we are estimate the difference between epsilon gamma minus epsilon gamma of kt over epsilon n, this is bounded by some constant, which is the bound for the velocity times t over epsilon n. That's the time for the case piece. And we have an actual epsilon floating in front. So in the end, for each piece, the difference for the input is C times epsilon times T over epsilon n. And then we use the fact that L is uniform Lipschitz in the first slot. So together with the fact that the integral here has length T over epsilon n, and there's an actual epsilon in front of the integral, the total arrow is expressed here. Okay. And we can clean things a little bit. And we see the arrow introduced by fixing the first law, which is the macro scale variable. We have some constant C times T squared over n. So this is the first type of arrow. And next, we are going to relate the first sum here with our metric function m. In particular, m is the minimum cost for you to go from one point to the other. And by definition, we see here, we can look at the m function that starts at the starting point of our gamma function at the case piece, the starting point for the case piece and the ending point for the case piece. So our curve gamma is taking time T over epsilon n to go from the starting point to the ending point. Our m function is the minimum cost to do so. So by definition, it's definitely less than the integral above with this particular curve gamma. Okay, so let us clean things a little bit. So this is what we have. We prove U epsilon is greater than this summation of our metric and together with the arrow term. Okay, so next, for each m term here, we can use what we had before because now our first law is fixed, and this is exactly the case where we have H only depends on Y and P. Even though this term looks very complicated, this is just the result with the correct term plugging in. And we can replace the epsilon m by T over n times L bar, which is the limit for the averaging metric. And the arrow is C epsilon. We have n terms. So in the end, when we use the previous result, we introduce another arrow of C times epsilon times n. So this arrow is caused by we averaging out the micro scale behavior, the homogenization process. And now we are at this stage where we have the L bar appears and it has a complicated inputs, but actually we can construct an admissible path for U, which means here I call it eta. Eta starts at epsilon gamma of 0 and ends at x. It uses time t to go from the starting point to x. And the running cost for my eta is almost the same as what we have in this complicated sum, except for the fact that in the first slot, I don't have a fixed value. I have eta of s. And for this admissible path, by the optimal control formula for U, we know together with the initial cost, the total cost for this path eta is greater than or equal to U of x comma t. So we are almost done by relating U epsilon and U, except for the fact that can we estimate how far apart are these two? If we can, we already relate U epsilon with U together with some arrow term. And in fact, we can estimate the arrow for these two terms inside the red box here. And we just, again, use the fact that L bar is Lipschitz in the first slot. And we use the fact that the velocity is bounded. We can show the arrow is constant C times T squared over n. Okay, so let's clean things up again. And so far, what we get is U epsilon is greater than or equal to U minus 2 arrow term. So here we have two types of arrow terms here. One is caused by fixing the macro scale variable, which is C times T squared over n. And then the other type of arrow is C times epsilon times n, which is the homogenization of microscale variable. We need to minimize the total arrow, which means we need to treat these two types of arrow equally. And we set them equal to each other, and we can show the optimal n is T over square root of epsilon. And if we plug in T over square root of epsilon, we can see the rate of convergence is OT square root of epsilon. In fact, in the actual proof, we need to take the integer because n is the pieces we cut our curves into. But all the technicalities can be handled and the result is true. Okay, so that's the basic proof for our results. And I want to mention the superadditivity of our metric function as promised in the beginning. So this superadditivity of our metric function can help us prove the theorem we already seen, which is the rate of averaging metric to its limit. So let's look at what is the superadditivity of our metric function m. So in particular, here, for simplicity, we start at the point 0 and we end at the point y. Okay, so we assume the absolute value of y is less than or equal to some constant m0 times time t. Okay, we can again view m0 as the upper bound of our optimal path, the velocity of our optimal path. And superadditivity says 2 times of the metric function, which is the cost for us to go from 0 to y using time t, is less than or equal to the cost for us to go from 0 to 2y using 2t, and plus some error term c. And this constant c does not depend on y or t. Okay, it only depends on the dimension m0 and our Hamiltonian. So this is roughly saying 2 times of the cost for us to go halfway is about the same as we go the full way to 2y. Okay, so why is this helpful? How does it help us to prove the above theorem? Okay, so the proof is like this. So I will show you how we can use this theorem to prove the above averaging metric rate of convergence, and then we will talk about how we can prove this superadditivity. So in particular, once I have superadditivity, I can iterate the whole inequality, and we can get 2 to the k times m minus c is less than or equal to m of 2 to the k times t, comma 0, comma 2 to the k times y minus the constant c. And then we divide both sides by 2 to the k and send k to infinity. So on the left-hand side, we have m minus c. On the right-hand side, as k tending to 0, we have m bar, which is the by definition. And we know m bar is equal to t times L bar with the correct inputs. Okay, I just cleaned up the intermediate steps, and this is what we get so far. And then after that, we can plug in t over epsilon for t and y over epsilon for y. And we multiply the whole inequality by epsilon. So on the left-hand side, we have epsilon times m minus c epsilon. On the right-hand side, we have m times m bar of t over epsilon, comma 0, comma y over epsilon. And this is equal to m bar of t, comma 0, comma y, which is the term we want, the limit t times L bar. Okay, this is exactly one direction of the theorem above about the averaging metric. And the other direction can be proved similarly by subadditivity. So I will skip that. So next, I want to talk about the superadditivity of our metric function m. The proof idea for superadditivity of m, it comes from a topological lemma of metric geometry by Burago. And this was first used to study the stable norms. And surprisingly, we are using it for our PDE problem. And this lemma can be viewed as a generalization of intermediate theorem in higher dimensions. So here following, I have the lemma stated here. So roughly speaking, this lemma says the following. So suppose we are in Rn, the n-dimensional space, and we have a continuous path, C. Then we can cut this path into smaller pieces. And with some of the pieces, we can glue them together and go exactly halfway. And moreover, the pieces we use to glue the new halfway path is not too large. So it's bounded by the dimension n plus 1 over 2. And this lemma can be actually proved by Boussac-Ulam theorem from topology. Okay, so next I'm going to do basically a picture proof using this lemma from metric geometry to prove the superadditivity. Okay, so we want to prove the inequality above. We start from the right-hand side, which is the cost to go from 0 to 2y using time 2t. So suppose gamma is an optimal path that starts at 0 and ends at 2y. And we also know the velocity of gamma is bounded. So in order to prove this inequality above, we have to relate to the left-hand side, which is the cost for us to go from 0 to y using time t. In other words, we need to manufacture a path out of gamma to go from 0 to y. And this is exactly where we used the previous lemma by Burago. We will cut this curve gamma into smaller pieces. So here the picture, I have some smaller pieces here, which is gamma of A1 up to gamma of B1, and then so on and so forth. So what we know from the lemma is if we glue them together, it will go from 0 up to 1. Okay, but the thing is we cannot randomly move paths around because it will change our cost. So the key idea here is we use the fact that the second slot for our L is periodic. That means if we move our paths by integer vectors in Rn, then the cost is the same. So the idea is we are going to translate all the smaller pieces we have so that the ending point for the previous small path and the starting point of the next path are within very small distance, say the n-dimensional cube. So like the picture showed down here. They are not exactly attached to each other, but they are very close. And also for the first piece, I'm going to move it so that it's very close to the starting point 0, but maybe there is some gap there. And then after that, we will glue them together using some small time. So we will just connect the starting point and the ending point for different pieces. And so that we can have a path goes from 0 up to y. And we can show that by doing this, we didn't change the cost much. So basically 2 times of the cost for this path is almost the same as the path we start with, which is gamma. And then we are done. And this is basically the proof for superadditivity. And I think this is the end of my talk today. Thank you so much for your attention.
Thank you, Yuxi. You use exactly 15 minutes. That's great. So other questions for Yuxi before we start the informal discussion?
So I have one question. You said
Yes.
the superadditivity constant you have is independent of the C you fix in the X slot. So
Right.
that is due to some which assumption is it? Is it the Lagrangian you have some uniform in X rate
Yes,
of
yeah.
growth? Okay.
Right, yeah, so we need the assumption for L and H is uniform Lipschitz in the first slot.
But is it that, or because here it's about the the metric, right? The cost.
Right,
It's a uniform in growth of the Q, right? L.
right.
I can see how you use uniform Lipschitz when you do the cutting, but here I don't see the.
Yeah, so for this proof, I think it's very similar to the curve cutting we just seen. So like whenever we are cutting the curve, we have to make sure the error is not too large by using the uniform Lipschitz constant of L. For this theorem, independent of little c, basically we use the same idea, and because of the uniform Lipschitz in the first slot, no matter which little c we had there, we can control the arrow to be the same.
Okay.
Yeah. I agree that that's a strong assumption, right? Because if you put like the Hamiltonian is AXY times the length of P, then it doesn't satisfy, right? But I mean, it comes with the cost that, they can control it uniformly, right? Yeah, but I agree, it's a strong assumption. Right.
Thanks.
Are there other questions? So if not, then let's thank Yuxi, and then let me stop recording, and then we start our informal discussion.